In the previous video, we introduced the concept of a rotation matrix. In this video, we apply eigenvector-eigenvalue analysis to a rotation matrix, and we find that its eigenvalues are complex. We determine the eigenvalues and eigenvectors of this rotation matrix. Write an equation to solve for the eigenvalues lambda by attaching minus lambdas to the elements on the main diagonal and forming the product of the off-diagonal elements. Rewrite the result as a quadratic equation in descending powers of lambda. Please pause the video to check that the two solutions obtained using the quadratic equation are cosine of theta plus I sine of theta, which we call lambda plus, and cosine of theta minus I sine theta, which we call lambda minus. Using Euler's formula, we abbreviate cosine of theta plus or minus I sine of theta as e to the plus or minus I theta. These eigenvalues have real and imaginary parts. They are complex. Focusing in on the upper row of the rotation matrix and substituting in the eigenvalues lambda plus or minus, we can rewrite an equation that relates the x and y vector components. Plugging in the lambdas and performing some algebra, we obtain eigenvectors with components 1 and minus or plus I. Overall finite scalar multiples of these values are also correct. Using these two vectors as a basis, we can express some generic vector w as a linear combination of the vector with the minus I component and the vector with the plus I component. A hallmark of a rotation matrix is the presence of complex eigenvalues and complex eigenvector components. In the notational convention we have adopted, the signs seem to be visually mismatched. The plus and minus in the weighting coefficients w plus and w minus correspond to the plus or minus signs attached to lambda, which confusingly, but correctly, are the reverse of the minus or plus signs attached to the i's in the vector components. Using the eigenvectors of the rotation matrix as a basis for expressing a generic vector w allows us more easily to analyze the effect of applying the rotation operator to the vector w. Hitting vector w with the rotation operator r hat multiple times corresponds to hitting the column vector representation of vector w with the corresponding rotation matrix the same number of times, which corresponds to hitting the individual pieces of the column vector representation with the rotation matrix multiple times and tickling out multiplicative factors of the eigenvalues lambda plus and lambda minus. This process resembles shaking fruit from a tree. Applying the rotation operator r hat n times corresponds to taking the eigenvalues lambda plus and lambda minus to the nth power. Substitute in the expression for the lambdas in terms of complex exponentials, and write the power n as part of the superscripts of the exponentials. We obtain e to the I times n times theta and e to the negative I times n times theta. Because we obtain this expression by considering a rotation matrix, we expect that this expression describes vector rotation. However, given the complicated appearance of this expression, it is instructive to confirm that this expression, with complex exponentials taken to the nth power, describes rotations. Consider the simple example in which w plus equals w minus equals some finite variable w divided by 2. Write out the first component of this column vector by visually following along with the yellow highlighters. Do the same to write out the bottom component, which has the imaginary root I. In the bottom component, multiply outside and in the denominator by the factor I. 2 powers of I yield a negative 1, which cancels out the negative sign already out front. use Euler's formula to re-express the complex exponentials in terms of trigonometric functions. Here there is a minus sign in the middle. The plus I sine of n theta to the left and the minus I sine of n theta to the right cancel. Similarly, re-express the complex exponentials in the bottom component in terms of trigonometric functions, again taking care to recognize that the negative sign in the exponent corresponds to a negative sign here. Noticing this negative sign, we see that the cosine terms, instead of the sine terms, now cancel. The two copies of cosine in the top component divided by 2 give one copy of cosine, and the two copies of sine in the bottom component divided by 2 and with i's canceling out give one copy of sine. When n equals 0, the vector w is aligned flush with the x-axis. As n increases, the cosine and sine components of the vector w walk around the circle. As a reward for the effort we invested to carefully analyze this system, we now see that a dynamical system with complex eigenvalues and eigenvector components, which can be written in a messy format, can have dynamics expressed in a simple format in which trigonometric functions describe rotation in space. Notice that for the particular initial condition studied here, the components of W are purely real. Neither of the components explicitly contains the imaginary root I. In this example, the initial vector points directly to the right. How should the coefficients W plus and W minus be modified to represent an initial vector pointing at an arbitrary initial angle relative to the x-axis? Can you plot the eigenvectors with components 1 and plus or minus I on the xy plane? Why not? Please pause the video to consider these questions. In the previous video, we introduced the concept of a rotation matrix. In this video, we illustrated that a rotation matrix has complex eigenvalues and complex eigenvector components. And we confirmed that a complicated expression defining a vector in terms of complex numbers taken to the nth power can, in fact, represent rotation. If it turns out that a system has complex eigenvalues, this is a hallmark indicating that the dynamics of the system can be represented by something that looks like a rotation matrix. Thus, the system might support dynamics that correspond to oscillations having sustained amplitude. Complex eigenvalues can also correspond to oscillations of increasing or decaying amplitude, and the exploration of these cases along the lines of the discussion in this slide deck is left as an exercise for the viewer. The understanding of rotation and related matrices developed in this video and the accompanying homework is helpful for identifying dynamical systems in physics, engineering, and biology that support oscillatory dynamics.